Hello everyone, I am Kiet, and I will introduce the paper Universe of Few Short Learning Dense Prediction Task with Visual Token Matching. The definition of dense prediction task is to learn a mapping from an input image to a pixel-wise annotated label. You can see some example here. There are two issues of previous methods on these tasks: costly pixel-wise labeling and not generalized to an arbitrary task. To design a universal few-shot learner, two properties should be satisfied. Task agnostic architecture. Architecture should handle arbitrary tasks, sharing most parameters across tasks, and not exploiting task-specific prior knowledge or inductive bias. Adaptation mechanisms should be flexible to work on a novel task and efficient to prevent overfitting. Inspired by the cognitive process of analogy making, visual token matching based on similarity in image patches to combine label patches for prediction. Here's the problem setting for VTM, where F is a universal few-shot learner working on a query image and a superset. The challenge of this setting is that tasks have different output structure. So the author casts a task into C single-channel subtasks. This is the overall architecture for the few-shot learner. Let's look at the first module, image encoder. It receives an image X in the form of M patches. It has two set of parameters. Theta is set across tasks, while theta t is the specific to each task. The next module is label encoder, which will encode the labels from superset. Both image and label encoder use the same VIT architecture. The matching module will perform matching between image tokens at multiple hierarchy to synthesize prediction in embedding space. In this module, the encoded query image will attempt to encode the support images via multi-hop attention to produce similarity for combining encoded label patches for prediction. The last module is a CNN label decoder, which fuse multi-scale output from matching module to produce final output map. The whole prediction process is wrapped in the zero box. After getting the output from the model, loss to be computed for training. At each episode of a task, the model is trained to predict labels in a query set using a superset for the task. Loss can be L1 or gross entropy loss. During inference time, the bias parameters should be fine-tuned on a sub-superset and a sub-query set of a new task. Then the model is evaluated by predicting label of unseen queries in the test dataset. Next is the main results in the paper. From the quantitative comparison of VTM with other baselines, VTM outperforms all few-shot baselines by a large margin. It works competitively with supervised baseline on many tasks. With only 10 support images, VTM performs better than fully supervised INVPT. Regarding the qualitative comparison, few-shot baselines catastrophically underfit to novel tasks, while VTM can robustly fine-tune thanks to parameter efficiency of the adaptation. Moving to the next figure, it shows that VTM with more additional support data can reach or surpass supervised methods on many tasks. In conclusion, the paper introduced a novel and intuitive approach to solve arbitrary dense prediction tasks with few-shot learning. VTM is non-parametric, can adapt flexibly to a new task with minimal task-specific parameters fine-tuning, while the training knowledge is not forgotten. VTM shows strong few-shot performance comparable to supervised methods. The method is potential for various domains, including ones in vision and multimodal. However, the limitation of VTM is low inference time due to computation from label encoder and matching module.